Welcome to Easy BTech. I'm Dr. Gayatri. I'm going to explain about Davisson and Germer experiment. This experiment is a practical evidence for matter waves that was given by Davisson and Germer. This is the experiment that proves the de Broglie's hypothesis. De Broglie's hypothesis was only a theoretical assumption, but this is an experimental demonstration. So I'll be telling you with a very easy way of this so that you can easily remember it like a story and present it in your exam. So do focus towards easy BTech concept on Davisson and Germer experiment. Okay, now let's go into the experiment. This experiment mainly consists of three parts. One is electron gun. First one is electron gun. The second one we have is target. Here the target is nickel crystal. Nickel crystal is chosen as target. And the third one is we are having here a Faraday cylinder which is mounted on a circular scale. When I say here circular scale, you will be having this Faraday cylinder to be moving on the circular scale in all the directions to capture here all the electrons that have been reflected in the different directions. We will make use of this Faraday cylinder and we will mount it on a circular scale. Okay. So here electron gun will be giving you or giving us production of electrons which will be allowed to incident onto a target, and these reflected electrons will be collected by means of a Faraday cylinder which is keeping on moving on the circular scale. So let's have a look over the figure. You are having here a circular scale. This is your circular scale. On this circular scale, I am having here an electron gun to be placed over. This electron gun has a sharp filament F, and this one is having a pinhole through which the beam of electrons could be passed. To have a sharp beam, this point which we have selected on the plate should be very sharper. And then we are having these electrons to be directed towards a target. The target that we have chosen here is nickel crystal. This is our target. Now what is going to happen? Once these electrons are incident onto this target nickel crystal, they keep reflecting. So to collect these electrons that have been reflected, we are going to use here a Faraday cylinder. We are going to mount a Faraday cylinder on this circular scale. This is our Faraday cylinder. Yeah. This Faraday cylinder is in turn connected to a deflection galvanometer so that it can measure the angle of deflection. To measure the angle of deflection, a galvanometer is connected to Faraday cylinder. Since I said here it is a scale, I'll make it in the form of a scale. So like this, you will having this to be a scale, circular scale. This is your circular scale. This is how we have here the construction of Davisson and Germer experiment. So I repeat here, you are having a filament F provided for an electron gun. When this filament is heated, we are having electrons to be ejected. These electrons which have been ejected pass through the pinhole of the plate. Say that you have some pinhole here with the point O. This pinhole makes only a sharp beam to be outside and incident onto your target. The target is nickel crystal as we have said. Once these are incident onto the target, what will happen? They keep reflecting. Once they are reflected, it is collected by means of a Faraday cylinder. This Faraday cylinder is in turn connected to deflection galvanometer to measure the angle of deflection. And another important thing that we need to acknowledge here is that this Faraday cylinder is provided with insulation from inside. It has some insulation from inside. This insulation helps it to collect only fast moving electrons. To collect only fast moving electrons, we have an insulation to be provided for this Faraday cylinder. Now, as I said, once we apply here the voltage, the filament gets heated and it generates you the electrons onto the target, which are being collected on the with the help of Faraday cylinder that is moving on your circular scale, that keeps moving on your circular scale. Now, when this is happening at a potential, that is your voltage of 54 volts, it has been observed that first order diffraction with the highest intense peak is observed. Highest intense peak is observed. So generally here this process starts at about, that is you are having bump in the curve, will be started around 44 volts itself. If this is your scattering, you will be having this to be started around 44 volts itself. But we can have here around 44 volts. A prominent beam to be observed at 54 volts, and at that point the angle of deflection here that we will be observing is 50 degrees. So this angle is 50 degrees. And this is happening at a which voltage? It is happening at 54 volts. And since we are having this to be having, at this voltage to be having the highest intense peak, this expression we are going to consider now. Since we are having this to be a crystal, this has lines here, nothing but you are having row of atoms which act like your diffraction grating. So in such a case, we will be making use of your Bragg's equation. So what is our Bragg's equation? 2d sine theta equal to n lambda. As I said, when are we going to have the prominent peak? For n is equal to 1. And here the angle of deflection, what did I say here? It is your 50 degrees. So this angle, whatever we are taking, is taken as 65 degrees. I'll tell you how it happens here. Just have a look over the figure. This is how we have the atomic planes of a crystal. Like this, we will be having the planes of a crystal. Okay. So, when you are having here ray of light to be incident here, it is deflected with an angle of 50 degrees as we said. So, drop a normal. This is a deflecting angle. So, what is the angle that is made with the plane? Since this is normal and this is become your 25, and this is a normal drawn to the plane. So, this is your 90 degrees. So, how much will this angle be? This angle becomes 65 degrees. 90 minus 25. So, you are having theta equal to 90 minus 25, which will be giving you 65 degrees. And your D is spacing between the planes. So now if I substitute these values in the Bragg's equation, it is 2 into 0.91, the spacing between the planes of a nickel crystal, and sine 65 with n is equal to 1, because I said it happens at first order diffraction, n equal to 1. So you will be having here lambda equal to so much. If I simplify, this value is approximately around 1.64 Armstrong units. Now, we know from your de Broglie's hypothesis that de Broglie wavelength is given as 12.26 by root V. Hope you can recall this formula, and this V represents voltage. So what is the voltage for this highest order diffraction with the highest intense peak? It is 54 volts. So I'll write it as 12.26 by root 54. So So when I simplify, it is also once again around 1.66 Armstrong units. 1.66 Armstrong units. So from the experiment, I got it as 1.64, and from de Broglie's relation, I got it as 1.66 Armstrong units. So once we are looking at both the values, in both the cases, the wavelength is same, which concludes that the wavelength of electron beam calculated from Bragg's law and de Broglie's are in good agreement. They are accurate, they are the same, which confirms de Broglie's hypothesis. So this is about your Davisson and Germer experiment. So if you are mentioning with the three parts and then with the figure, you can easily write the story of Davisson and Germer experiment. Hope the video will help you out in foster learning. So like, subscribe and share for easy BTech for you. Thank you.